Well, we're going to keep chugging along here in chapter 16.6 now on surface integrals. And the problem that we're going to do, I'm going to split the section up into two sections. The first one is going to be when we deal with scalar functions, or just regular functions. And the second video then we'll talk about what happens when we're trying to find surface integrals over a vector field. So all that 16.5 stuff was preparation for this right here, and I don't really think you're going to see many of the problems given in this first video terribly often. But let's just take a look then. We're only going to solve one problem, and we're going to solve this one problem in two different ways. So we're going to look at 16.7.7, which is the following. You have h of xyz is equal to yz, or that's the wrong problem, is equal to x squared root 5 minus 4z over the parabolic dome. Z is equal to 1 minus x squared minus y squared. So how are these integrals then different from 16.5? And let's just take a quick aside, right? And let's look at some formulas, right? Surface integral formulas. So it's the exact same. You have three conditions. The first condition is when your surface is parametrized surface, right? So then you take the double integral of over the surface of some function, let's call it g of xyz, d sigma. All right, I know in this problem we called it h, but it doesn't matter, right? H is just the name of the function, and so here in this general form we'll just call it the function named g. Then g of xyz d sigma is equal to the double integral over r of g times f of u of v, little g of u of v, and h of u of v, and then ru cross rv, the magnitude of that, du dv, right? And this is where we parameterize our surface, right? Surface gets parameterized into r of u of v is equal to little f of uv, little g of uv, and little h of uv, right? So we just take these guys and we throw them into the function. And so, yeah, we're going to do the example of this with the problem I just gave. The second one then is when you have an implicit surface. All right, so remember what an implicit surface was, right? And then this double integral of g of x, y, z d sigma over the surface is equal to the double integral over the region of g of x, y, z, and then you have this nabla or del f over del f dot p dA. And remember, p is some unit normal to dA, right? So if dA was dx dy, then p would be the k vector, or 0, 0, 1, right, in the z direction. So so that's an implicit surface. Again, if you don't remember what an implicit surface is, go back to 16.5, and I covered that stuff there as well. And then thirdly, we have an explicit surface, which then this double integral of s of g of x, y, z d sigma is equal to double integral over r g of x, y, f of x, y times the square root of f partial x squared plus f partial y squared plus 1 dA. And remember, right, that so not remember, but so these all look really similar to just your surface area integrals, and that's essentially what's true, right? Because remember, g of x, y, z is a function, okay? So so we just introduce a function in front of d sigma, and then so we're not just finding surface area anymore, but we're finding a surface integral. And keep this in mind for these types of problems. We're dealing with functions in this video, okay? And in the next video, then we'll consider the other case. But anyways, I digress, and we hop back over to 1667. So what are the two ways, right? What are the two ways that we can do this problem? Well, we can actually do it in all three ways, but I don't really want to do the implicit way. I did an implicit example in the previous video, and so it's not going to be terribly hard to do that here. You guys can try it yourself. But let's do it then the explicit way first. Right, and the reason why I want to do explicitly first is because the parabolic dome, this is an explicit function, right? This is essentially going to be f of x comma y is equal to 1 minus x squared minus y squared. So, all right, so the explicit function then is then the double integral over the surface of h of x, y, z, d sigma, is going to be the double integral over the region of h of x, y, and now z became f of x, y, right? You can see that here z became f of x, y, so that's why we replace it with that, dA. And in our case, right, okay, so what does this mean? Well, it just means that wherever I have a z, I need to replace it with f of x, y, which is 1 minus x squared minus y squared. So what do I have? I have a double integral, okay? H was x squared root 5 minus 4 times, not z, but right, I need 1 minus x squared minus y squared. Okay, and now I need, oh, whoops. Now we need, sorry, this, I had the wrong formula, but this is f partial x squared plus f partial y squared plus 1 dA. So now we need to find this guy, right? We already found this guy right here, so this guy was all this. And then f partial x is going to be, well, negative 2x, right? So this is going to be times the square root of negative 2x squared plus f partial y is also negative 2y squared plus 1. And then dA at the end. Okay, so let's just say dx dy for now. And then now you get double integral. This becomes x squared square root. This is 5 minus 4, which is 1, and then plus 4x squared plus 4y squared. This becomes 1 plus 4x squared plus 4y squared. And this is multiplied by, well, this becomes 4x squared plus 4y squared plus 1, which is the exact same thing as these two guys, right? These two guys are the exact same thing. They're both under square roots, and there's a dx dy. And so now this becomes a double integral of x squared times 1 plus 4x squared plus 4y squared. And there's no square roots anymore because they killed each other, right? The two square roots here cancel each other out, and so we're just left with whatever in the square root. Okay, and so the reason why I just randomly assigned dx dy is because now we want to convert this, right, into polar. So again, why am I converting, you might ask, right, why am I converting d sigma, right, into something polar? Well, we converted d sigma into dx dy first, right? By the way of, if you just look at this equation right here, there are only x's and y's in this integral, which means I have to, my dA has to be dx dy or dy dx, right? Look, this thing here only has x's and y's. Everything is an x or a y or a function of x, y. So the idea then is after you convert to dx dy, only when you go from dx dy to polar is when you convert, when you have to add the r. So that's what I'm trying to do here. So now we get r squared cosine squared theta, right? 1 plus 4r squared. Now I need r dr d theta because I'm going from dx dy to dr d theta and not d sigma dy to dr d theta. So if I go from d sigma to dr d theta, then I do not need to convert with an extra r term. But when I go from dx dy, right, I have to go to r. So essentially what happens is I went from d sigma to dx dy using this formula right here for the explicit surface, right, the explicit surface formula. And then because the explicit surface formula is in dx dy, then this is hard to evaluate, so I'm going to then evaluate it in terms of r's and thetas. And so now we need the penalty term for that conversion, which is r. And then, okay, so now, what are my bounds, right? And so remember how we set up our bounds? We set up our bounds by looking at where these guys intersect, and I forgot to write z is also greater than or equal to 0. So we want to look at where our z surfaces intersect, right? And that's how we find our bounds, because then we're in the xy plane. So if I look at these two guys, we have 1 minus x squared minus y squared is going to be equal to 0, and you'll see 1 is equal to x squared plus y squared. And what is this? Well, that's just equation of a circle centered at the origin with radius 1, right? So that means my bounds then are going to be r going from 0 to 1, and theta is going from 0 to 2 pi, right? Again, I found my bound, my theta, r and theta bounds by looking at where my surfaces intersect. Okay? And now it's just time to do this integral. So this becomes really the integral from 0 to 2 pi, 0 to 1, r cubed of cosine squared theta 1 plus 4r squared. Okay, dr d theta. I multiplied this r in to here and got an r cubed. Okay, so let's see. What's an easy way to do this? I guess, I mean, we just got to pound this out. So that's equal to then 0 to 2 pi, 0, 1, r cubed cosine theta plus 4r to the 5th, cosine squared theta, cosine squared theta. Okay, and so I just distributed dr d theta. Now integrating with respect to r, I go from 0 to 2 pi. This becomes r to the 4th over 4 cosine squared theta plus, this becomes 2/3 r to the 6th cosine squared theta. Okay, and of course I need to evaluate this then from 0 to 1. Okay, and that becomes, well, if you plug in 0, you don't get anything, so then 0 to 2 pi, and this becomes 1/4 cosine squared theta plus 2/3 cosine squared theta, d theta, and so that's equal to 1/4 plus 2/3 is 3 plus 8, so 11/12, and I'm going to pull that out in front, 0 to 2 pi cosine squared theta, d theta, and now cosine squared is 1 plus cosine 2 theta over 2, right? So it's really this integral, and that's, or this is a 2 pi, and so if you actually calculate this integral out, you'll see that it's 11 pi over 12. Okay, so that's how we do it explicitly, and so now let's do it then with the parametrization way. So this was the explicit way, and now we'll do it parametrizing. And yeah, so it should be fairly similar, right? So, okay, so I have this parabolic dome right here, right, highlighted in this blue. And how should I parameterize it? Well, kind of give it away by doing it explicitly, right? We should probably use cylindrical coordinates. And so what do I get then? I get s of r and theta is going to be r cosine theta for x, r sine theta for y. And remember, z was equal to 1 minus x squared minus y squared. So then this becomes 1 minus r squared for z. All right, and now we need SR cross S theta. So SR is equal to cosine theta, sine theta, negative 2R, and then S theta is going to be negative R sine theta, R cosine theta, 0. And now SR cross S theta is equal to what? It's equal to the following. IJK cos sine negative 2R, negative R sine, or negative R sine, R cos, and 0. And then, okay, this becomes 2R squared cosine theta, comma, 2R squared sine theta, comma, R. Okay? And then, now what? Okay, so that's the cross product, and now we need SR cross S theta, because, look, if we go back to the parameterization equation, right, So I found my parametrization, which now I know what these guys, I know what G of U and V, I know what F of U and V, I know what H and U of V are, but I need to find RU cross RV, right, the magnitude of that. So now I need to find the magnitude, which is what? It's the square root of 2r squared cosine theta squared plus 2r squared sine theta squared plus r squared, and that's equal to 4r squared cosine squared theta, or 4r to the fourth, plus, actually, is it 4r to the fourth or 4r? Yeah, okay, yeah. Plus 4r squared sine squared theta plus r squared, or 4r to the fourth sine to the fourth theta. Okay, and then that's equal to root 4r to the fourth plus r squared, which is equal to r times 4r squared plus 1. Okay, so that's SR cross S theta, the magnitude of SR cross S theta. And now, the double integral of g of x, y, z, or in our case, again, it's h. It's just the name of the function. D sigma over the surface is equal to h of f of uv, g of uv, h of uv, little h of uv, ru cross rv, du dv. Right, and so that becomes, all right, h, remember, h was equal to x squared root, what was it, x squared root 5 minus 4z. Okay, so what is h now? H becomes x squared. So I need to plug in, right, this is little f of r theta, this is little g of r theta, and this is h of r theta, right? And so our u's and v's are really r's and thetas. U's and v's are like placeholders for your parametrizations, right? So now this becomes, okay, h was x squared minus root 5 minus 4z. So x squared becomes 2r squared cosine theta squared, right? Root 5 minus 4z, which is 4r squared, if I'm not mistaken. 5 minus 4z. Did I? Oh, wow. I'm being really dumb. No, that's not right. That's the cross product, right? This is f of uv, or r theta, right? It has to come from the parametrization, not the cross product. I was taken from the cross product. That's wrong. This is g of r theta, and this is h of r theta. All right, that makes a lot more sense. Okay, so that's wrong. Erase. So it's x is r cosine theta squared, root 5 minus 4 times z, but what's z? Remember, z is parameterized as 1 minus r squared. Okay, and so then that's 1 minus r squared. And then I multiply it by ru cross rv, which we found right here. We called it sr cross s theta. So that's r root 4r squared plus 1. And now du dv is dr d theta. And so look, we went straight from d sigma to dr d theta, so I don't have to multiply another r in here. Okay, it's only when you go from dx dy to dr d theta do you need to multiply the r. So now I have this, and what is this? This is the double integral then of r squared cosine theta, or cosine squared theta. This is root 1 plus 4r squared, and then times r root 4r squared plus 1, dr d theta. And we're back in familiar territory, r cubed cosine squared theta times 1 plus 4r squared, dr d theta. And what does this integral look like? This integral looks a hell of a lot like this guy up here. Zoom out, please. Zoom out. There we go. It looks a hell of a lot like this guy right here, right? In fact, they're the exact same integral. So, yeah, so you can set up either way. You can parameterize. You can use the explicit way. They both will get you the same answer, right? We got to the same integral. All you need to do is set up the bounds, but you set up the bounds in the same manner as we did up here, right? You just look at where these guys intersect, and then you parameterize this guy accordingly in terms of r and theta. And yeah, that's going to be it, I guess. Actually, let me go back and say something about the bounds here, because when you parameterize this guy, you really want to give the bounds here, right? So if you want to say r is between, right? So when you parameterize s, then you want to say r is between something, and theta is between something. Theta is between 0 and 2 pi because there's no constraints in the xy plane. And then what is r in between? Well, I know that z has to be greater than or equal to 0 as well, right? So then r can at most be 1, okay? And r can't be less than 0, because if r is less than 0, you get negative radius, which doesn't make any sense. So r is between 0 and 1. And yeah, so then you get the same bounds, then 0 and 1, 0 and 2 pi, right? Exact same bounds. So setting up the bounds for parameterizing is just, it seems a little bit different, but it really isn't compared to explicitly finding the bounds on the surface. But in any case, so this is how you do the surface integral. And remember, this is all when we have a function, right? We have a function. So that's the big highlight of this first video. In the next video, then, we're not h of x, y, z. It's not going to be h or g, but it's going to be f of x, y, z is a vector field. And remember how a vector field is different from a function, right? A vector field, then, which is the next video, and I'll introduce this in the next video again, right? F of x, y, z is equal to something like that, right? You have 3 entries. It's not a function anymore. And so what happens when you have a vector field? Well, shit gets a lot harder. And yeah, we'll take a look at that in the next video. See you guys there.